Welcome back. Let us continue with our learning. We were at the demo when we finished the first session. Let us go back to our command prompt and run the programs which we saw earlier. So here am I at the command prompt, and I have compiled all the code which I downloaded from the website. And then let me first run the display file. I'd say Java display file. The application, the program prompts me that I need to use it like this. I used to say Java display file and then the name of the file to display. I need to pass an argument here. So let me type in now Java display file, and then I would say display the same file, display file.java. Use the program display file in Java and display the file display file.java. I hit enter. So what the program has done is it has read the file display file.java, and then it has used the file input stream to read 1 byte at a time and print the contents on the screen. Now let me go to my editor. I will create a new text document. Let's say hello world. Programming IO is fun and easy. And then let me save this in C:. We'll call this sample. Already have sample2.txt. Okay, it is saved in C:. It is saved under C:, and I call it sample2.txt. Now what I'm going to do here is clear the screen first, and then I'm going to say Java display file, and then the path C:, sample2.txt. Here is the contents from the file on the screen. So we had C:, sample.txt. We had some text which is now printed on your screen. So what display file does is it uses a file input stream to read the contents from the file 1 byte at a time until end of the file is reached and print the contents on your console. Now let us use the second program, copy file. I have to use it like this. I have to give the source file and the destination file. Let us say I want to copy Java copy file C:, sample2.txt, and to let's say C:, again sample copy.txt. So what we have done here is we have copied the contents of sample2.txt to sample copy.txt. Now let us check if it has indeed copied. We'll use the program one more time, Java display file, and then we'll give the path copy.txt. display. Oh, my mistake. It should have been Java display file C:, sample copy.txt. Yes, it is indeed copied as shown by the program here. So these are two simple programs to copy a file and display a file. Let us look at how to use byte array streams. In this example here for byte array streams, we have a text, the quick brown fox jumped over the lazy dog. This is a string for us, and that string will convert into a byte array, and using a byte array output stream we are going to write the contents to a file called test.txt using the write to method. Okay. So let's try this program, Java byte array streams. It is copy. Now let us check it up. Display file, and then I would say it's the file name is called test.txt as given here, right? Test.txt. We have the contents of this string converted to a byte array and then written to the byte array output stream, and using the write to method written to the file output stream. The file name is given by test.txt. Time for us to continue. Let us look at buffered streams. We know that in OS terminology, every IO operation causes an interrupt on the system. Whenever an IO request happens from a program, the process has to suspend its execution and hand over state to the operating system. The operating system then will read the data from the location, memory or socket or file, or write data to the location depending on the case. Let us look at a schematic representation here. You have your Java program, which is a process as far as the operating system is concerned. Your Java program is a process. Similarly, there are multiple processes running in your system. You could have, for example, a printer device program, the screen display, your music program. All these are processes which are executing concurrently in your system. Remember, whatever program you write, your Java program or your C# program or your C++ program is converted into a process. The computer architecture does not talk about programs. They talk about processes. Ultimately, every program you write is a process, and processes have a unique process ID called the PID, and they also have a specific area in the heap memory. In the heap memory, we refer to the random access memory or the RAM. Now, let's say we have processes P1 and P2. Process P1 can access the contents of the memory area M1, and process P2, for example, would have only access to the memory area M2. It is forbidden for P1 to access the memory area of another process. So, now that we understood processes, process IDs, and process memories, let us see what happens when we do an input-output request. Now let us say this is your Java program reading the contents from a source file and copying it into a destination file. Now remember, we said your process can access only the process area M1. Your file resides in the file system. It is in the hard disk. Let us say it is in your C: or in your home directory. Now if P1 wants to read a file, the contents of the file have to be copied from the file system to the memory area M1. And that is what the operating system does. Whenever you use the file input stream to read a file, an interrupt is caused and a request is sent to the operating system, which will then copy the contents of the file given by your path, and the contents is copied into the memory area M1. Remember, M1 is a small area, and as you continue to read the file, more and more data is read from the file system and copied into your memory M1. So whenever you want to read a file, we actually cause an interrupt on the operating system. Similarly, for writes, we write to the memory M1, and then from M1 it is copied to the file system in the case of a write. So this input-output operations are no doubt expensive, and they cost a toll on the computer's resources. This transfer of control to and fro between the process and the operating system causes a strain on the processor, thereby reducing the resources for other concurrent processes. Always remember, there are other processes competing for the operating system resources, and it should be fair on our part to not monopolize any of these resources. So this transfer of control to and fro between process and operating system by means of interrupt no doubt causes strain in the processor. To make things easy, Java provides a beautiful abstraction in the form of buffered streams. Here, in buffered streams, data is read or written to a stream in blocks and not in bytes. We know that a block is composed of 512 bytes. So when buffered streams are employed in a program, that OS interrupts have the possibility to be reduced by a minimum of 512 times. For example, let us say you use a file input stream to read a file. When you say file input stream.read, 1 byte is read and copied to your memory. The next read copies 1 more byte. So this byte to byte copying or reading messages causes a strain on the processor. Since let's say you have file input stream and you have a read method that reads bytes one at a time until end of the file is reached. This continuous read is going to cause a number of interrupts on the operating system. When you use buffered streams, we're not going to read 1 byte at a time, but you're going to read ahead as one block. So the next time when you issue a read and if you're using buffered streams, what Java will do is, though you ask for 1 byte, it will copy the contents of the block and place it into the memory M1. When the next read happens, an interrupt will not be caused and the data will be read from the memory because it's already available in the memory as one block. This will continue until when you cross the 512th byte. Then what Java does is it copies the next block. So using buffered streams allow us to reduce the number of interrupts or operations we cause on the operating system. So how to use a buffered stream? Simply wrap the underlying stream in a buffered stream and you have optimization built into your code. The most important point to remember is whenever a read happens in the buffered stream, the block of data is read ahead, causing the next byte read to fetch the internal buffer and not from an OS interrupt. Okay, so far so good on buffered input streams. When using buffer output streams as well, the contents are written to the memory, internal memory, and the physical written only once they cross 512 bytes as one block. But when you're writing a file, we may have reached the end of the file before the 512th byte is reached, before the block is complete. So what we do in these cases is to use a flush method to form a physical write of the remaining bytes in the internal buffer. Here is an example. We have the file input stream and the file output stream, and then the file input stream handle fin and the file output stream handle ft are wrapped over a buffered input stream. We pass the fin and ft handles to the buffered input stream and the buffer output stream, and then afterwards we just do simple read and write. Now the read and the write are happening on the buffered input stream and the buffer output stream and not on the original file input stream and file output stream. So this way we have optimized the read and the write for block based IO. And always remember, when you're done with your write, you should do a flush on the buffer output stream so that whatever data is remaining in the internal buffer which is not yet crossed 512 bytes or one block, and end of the file is reached in between before that, and if end of the file is reached before that, those contents need to be physically written to the file system. So we do a flush. The decorator pattern is widely used in the Java IO class library. We decorate a file input stream with a buffered input stream. In this example here, we have the buffered input stream which is decorating the file input stream. This is possible because buffered input stream and file input stream have a common interface, and the buffered input stream is a composite of the file input stream. The buffered input stream has decorated the behavior of the file input stream by adding more functionality. Let us continue with data streams. While working with primitive data, we know that primitive data like int, char, float, we know that when working with primitive data, we know that primitive data like int, char, float, etc. have different representations in different operating systems. For example, in one particular operating system, an int can be 2 bytes. In another operating system, an int value could be 4 bytes. When we want to deal with primitive data types, Java recommends us to use the data streams. In this example here, we have the file output stream and the file input stream, and they are decorated by the data output stream and the data input stream. For example, if you want to write a short value, you should say write short. If you want to write an int value, say write int. And if you want to write a boolean value, say write boolean. If you want to write a string, use write UTF. The corresponding methods on the read are read short, read int, read boolean, and read UTF. The read methods, the different read primitive methods are available on the data streams. The data input stream for read, the data output stream for write. So this way, the underlying difference between different operating systems and architectures is taken care of by the JVM. If you want to store an integer in Windows operating system, you will similarly, without fail, store an integer in the Linux operating system. The internal intricacies of the allocation, the byte sizing is all taken care of by the JVM. So, data streams is an abstraction over primitive data types. So what we have seen so far, we have the file streams, which is an abstraction over the underlying file system. Could be FAT32 or NTFS. Then we looked at byte array streams. And then we looked at how to use buffered streams for optimized behavior. Now, using data streams, we have an abstraction on the primitive data types. So we need not worry about how integer representation or any primitive data type representation is different between different operating systems. So what is UTF? We know that ASCII data is represented as 1 byte, but in some European and Indian languages, we need at least 2 bytes to represent all the characters of the language. And in some Eastern Asian languages like Chinese, Japanese, and Korean, we need at least 3 bytes to represent the language alphabets. So depending on the regional settings of the host system, the operating system either allocates 1, 2, or 3 bytes to represent one character data. When we use UTF encoding for strings, Java uses the operating system defaults and uses either 1, 2, or 3 bytes to represent character data. So we need not worry about whether we should use 1 byte, 2 byte, or 3 byte. When we use write UTF and read UTF, Java takes care of the underlying regional settings on the executing computer system to allocate the appropriate number of bytes for the character data. So let us continue with the character streams. When working with text files, the main difference between the different platforms, Windows or Unix family, is the way new line characters handle. The new line is a /n is represented differently in different operating systems. It could be line feed, character feed, or just carriage return. We application programmers need not worry about that. If you're going to work with character data, Java recommends us to use the file reader and the file writer. If you want to read a text file, you create a new file reader, and since we are good programmers, we create a new buffered reader because we want to have optimization in our code. And on that buffered reader, we read line, and we continue to read a line until it is not null. Null denotes end of the file. To write a line into the file, we use the write method on the file writer. We use the write method, we pass in a string, the starting index and the length of the string. And since we are using a buffer writer, we do a flush. So file reader and the file writer give us an abstraction over the new line character. Remember, data streams, data input stream and data output stream give us an abstraction over the primitive data types. Now file reader and file writer give us an abstraction over the new line character. Let us look at object serialization. We always deal with objects. Everything we work or seem to do is related to an object. Now, how do we persist the state of an object? Java provides us with a convenient way to store the state of any object and fetch back the state of the persisted object. We use object streams for this. We have object input stream and object output stream. Again, we have the decoder pattern in action here. We create a file output stream and then we decode it with the object output stream. The object output stream has a method called write object, and we write the state of the object student1 and student2 into the underlying file system. Then we open the file using the file input stream, and then we decode it using the object input stream, and then we can do a read object to read back the student. Once we're done, we can print the values to see that we have indeed stored and retrieved what we actually had in the first place. Time for a demo now. Here is the file reader and file writer demo. The file reader is used to read, is used for text-based input-output. Let us look at the serialization example. We have a main method which is the entry point for the program, and we have students S1 and S2. We have Jack and Jill studying management and computer science. We create a new file called object2.scr and then write the object S1, write the object S2, and then we do a flush on the object output stream. Later we come back and read this file using the file input stream, the same file. What we wrote, we read it back, and then we decorate it using an object input stream, and then we read the object and we copy it into S3 and S4. Let us print the contents of S3 and S4 to see if they are indeed what we actually stored. It has to be Jack and Jill, management and computer science. Okay. So let's go back here and say Java. The name of the file is serialization example. So we opened a file, wrote the contents of the object, which is the state of the object, and read it back. One important point to remember here is, if you want to store the contents of an object, if you want to serialize the object, you need to implement the serializable interface. This is a marker interface, meaning this interface does not have any methods, but you should compulsorily implement this serializable. Without this, Java will throw you an error that the object cannot be serialized. Okay, so that brings us to the end of this session on input-output programming. To summarize what we have seen so far, first and foremost, we looked at streams. A stream is an abstraction over an input-output device. Why do we need this abstraction? It is because different input-output devices behave differently in different operating systems, and we, the programmer, need not worry about the final details of what happens between the device and the operating system. We have input streams and output streams. The file input stream and the file output stream provide us an abstraction over the file organization. It could be an NTFS file or a FAT32 file or any other new file organization. The JVM takes care of how the file is read and written to. Then we looked at byte array streams, which is optimized for writing and reading array of bytes. Then we looked at the buffered streams. Buffered streams provide us an optimization using block-based I/O. Then data streams, when you want to deal with primitive data, because primitive data differs across different platforms. So data streams provide us an abstraction over the primitive data. And we saw how UTF is used to, and we saw how write UTF and read UTF is used to write UTF data. Then we looked at text files and saw how the new line character is different in different operating systems and how Java provides an abstraction over the new line character using the file reader and the file writer. And finally, we looked at object serialization. We saw how we could have a file stream and write the state of the object using the object streams, object output stream, and read them back using the object input stream. The write object and the read object are the methods to write the contents or the state of the object and fetch back the state of the object. So, time for some self-evaluation. What is a stream? Why is there an abstraction for I/O programming? What is the difference between byte streams and character streams? How to read and write output using file streams? How EOF is identified? Why do we need buffered streams? What is block-based I/O? And how interrupts are caused? How is optimization achieved using buffered streams? Why is it necessary to flush a buffered stream? Why do we need byte array streams? Why do we need data streams? What is UTF? What is the difference between file input stream and the file reader? What abstractions provided by the file reader and the file writer? What is object serialization and how to persist the state of an object? And what is the decorator pattern and how is it used in the Java IO classes? I hope you enjoyed this session and we'll see you soon.